Yeah, I mean, I gotta do some magic, because, that's my Twitter handle. So if you want to send me questions, just go to the wizard Lucas. You can send your questions there. I'll answer you afterwards. I write things at lucasdacosta.com. I like to think I write well. Not sure if that's true. And today, we're going to talk about Lambda Calculus and about birds, which I'll explain in a bit. And I'd like to start this talk with a very philosophical question, which is, how do we know what we know? Like, how do we as humans reason about things? Because, many people like to think, they're very logical, that they use facts to get answers. And, that's not really that much possible, but people wanted to do it for a long time. And they tried it by creating systems, by creating ways of abstracting the real world and using symbols that they have very clear rules to manipulate so that they can get to conclusions. And many people worked on this. One of them was Leibniz, and the Leibniz dream was that if controversies were to arise, there would be no more need for disputation between two philosophers than between two calculations. So what he wanted was to settle all disputes with the use of logic. He said that it would suffice for them to take their pencils in their hands and to sit down in the abacus and say to each other, calculemus. So he wanted to settle disputes with this system of symbols that you have clear rules to manipulate, so there can be no disagreements. And we have that in our pockets today, right? We found ways of abstracting reality. We found ways of creating these systems which give us, which allows us to reason about things. And we have that in our pockets. That's our cell phones, right? And two other people that worked on that, and they're more related to the context of this talk, are Alan Turing and Ozone Church. So we hear a lot about Turing. So, Turing machines, state machines, all of that, which is what gave birth to the object-oriented paradigm. And there's also Alonzo Church, which is the guy that created what I'm going to talk about today, Lambda Calculus. And Lambda Calculus is what is behind functional programming, in the same way that state and Turing machines is what's behind object-oriented programming. And now, I know you're going to ask me this. Is it useful? Well, it is for me. So it helps you understand why things are made the way they're made. So it helps you, it enlightens you to think about many other questions, not only in the programming realm, but also in the philosophy realm. But you don't need to trust me. There's someone that you trust way more than me, right? So if you search on Stack Overflow for how helpful it is to know Lambda Calculus, and then you do what us programmers do best, which is go to the first accepted answer, of course, you read that if you want to program in any functional programming language, it's essential. Zoom in. If you want to program in any functional programming language, it's essential, right? Just a little bit more. Okay. I think I got my point across. So let's talk about Lambda Calculus, right? No tiers, only lambdas now. In Lambda Calculus, everything is an expression, which means that everything evaluates to a value. So in Lambda Calculus, everything comes down to this. And this token can be subdivided into 4 others, right? So we have 4 kinds of expressions. We have identifiers. We have abstractions, which are kind of like function definitions. You have application, which is just like function invocation, and you have grouping. And you use grouping to disambiguate things, as we will see in a bit. This is a lambda, lambda, people lambda. Meta variable is the argument it takes, and its body as well. Its body, pretty descriptive, right? And, well, when we call a function, when we do this, when we put 2 expressions, one next to the other, we say we're applying, in this case, arg to a, right? Just like when we use parentheses to invoke something in JavaScript. So when we do this, right, when we pass arg to that, to the identity function, right, just takes a and returns a, we get back arg. That's it. Simple. Lambda Calculus has no pluses, no minuses, none of that. It's just a way of manipulating symbols. It's a very clear system where you create abstractions and you manipulate symbols, and you get to an answer within that realm. The interesting thing about lambdas is that they can only take single arguments. So The thing is that if you want to work with multiple arguments, you can have lambdas that return other lambdas. So this is also called querying. So if you want to work with A and B, you can have a lambda which takes A, takes B, and you just return B. In JavaScript, this looks something like this. So you have a function which returns another function. More practical and very, very simple example is this. So if you have an add function, instead of taking two things at once, you can take one at a time, and you create another function which is called add2 in this example, which just takes 2 and adds 2 to any number you pass in, right? So when you evaluate expressions in Lambda Calculus, this is the syntax you use. You just use square brackets. In this case, we're replacing x with y. So we just replace all x's in the function body with y's, and that's it. Pretty simple. If you're trying to replace b in this case, it's not going to work, because b is not an argument. So you can only replace things that you take as arguments, right? That's how you evaluate, right? Each evaluation step is called a beta reduction, and we can only do beta reduction when expressions contain an applicative form, right? When we have beta reduxes. So if we're applying something to something, we can reduce it. When we have reduced it to the, so when we get to the most evaluated form, right, when we have nothing else to do, we call that the beta normal form. So this, how do you disambiguate this? Is it x with the result of z applied to y, or is it z applied to the result of xy? So application is left associative, which means that's what this disambiguates to, right? I'm not going to be spelling out letters, not really nice. But this is just like when you write proper functional code. So when you have a function which will return another function which takes another argument, if you do this, you're first applying first to fn, and second to the result of that. For you to disambiguate these lambdas, well, is this applying y to the identity function, or do you have a single lambda? Since abstractions extend as much to the far right as possible, that's how it looks like. So you have the whole lambda in that whole line. So this is why you might need parentheses to disambiguate, and that's what the last token I've showed you is for. And since Lambda Calculus is just another way of representing computation, and since Lambda Calculus is Turing complete, we can replace any programming language with Lambda Calculus, including JavaScript, right? Yes, that's what I'm going to do. So what I'm going to do is I'm going to write JavaScript as if it were Lambda Calculus, which means we're using no pluses, no minuses, no comparators, no booleans, none of that. Think of reserved word. I'm not using that. Okay? Just functions, no tiers. And I'm the first one to do this. Tom Stewart has done this in an amazing talk about Ruby, but I want to take it a step further. Not only going to ruin JavaScript, going to ruin JavaScript with birds, and then I'm going to ruin JavaScript and the birds. Hopefully, I'll apologize. We'll be friends. We can go for drinks later. So yeah, let's start replacing booleans. So I'm going to open the very best text editor in the world, also known as Vim. And sorry, zoom in. Oh yes, I can quit. I have the comments tattooed on my body, actually. I'm not kidding. I really do. Thank you. You can see pictures on Twitter. Not lying, really. Like, really. OK, so when I save this file, you're going to see the result here. Right? Whenever I save this file, you're going to see these dashes and whatever it's evaluating. So let's start with a boolean. Let's get a bool, right? So here I'm going to write a ternary. So I'm going to have true, which can just return yes or no, right? So if this is true, it returns yes, otherwise it returns no. It's very, very simple. So let's do this. What do we get back? Yes. If this was false, we will get no. Right? No mysteries. Now, the thing is, how can we replace this without using a ternary? How can we replace this only using functions which take one argument at a time? Well, what I'm going to do here is I'm going to do true first, right? So true, if you look at this ternary, what true does is it just takes two things and gets the first one, right? Easy. Which means that we can just have a function which returns another function, right? And this takes a and b, and true just returns whatever is the first thing passed to it, so we just return a. And now we can replace this with true, we can have yes, and we can have no. And now if we save this, we get back yes. Save this, yes, cool. Now if you want to get no, right, what would you do? Return the second thing, which means we can just come here, replace this by false, and we get no, right? Okay, so we have booleans without using any booleans. Good. We can also invert those booleans with a not, right? So you can take a boolean, which I'm going to call f, and well, since booleans are just selecting either the first or the second thing you pass to them, we can just invert the order that we apply the arguments to f. So you can just do f, b, a. And now if we have not false, this is true, this gives us yes. Okay, cool. It's easy. For now it's easy. we're gonna get there, don't worry. Okay. Replace booleans. Next thing, numbers, right? Now, what is a number anyway? Come on, what is a number, right? Well, when we see this, we think, oh, this is a number, but it's actually just a way of representing an idea, right? It's just an abstraction, right? This is one of the many ways we have to represent two. We can represent two in binary, we can represent two in hexadecimals. We need to dissociate representation and meaning. You know, what we want is to represent quantities, and we want to have a way of manipulating those symbols in whatever language we're using to get a result, right? That's what computation is all about. So how can we represent quantities with functions? Well, if we only have functions, well, we can just do functions. So 0 just takes f and x and never applies f to x. 1 applies f once, 2 applies f twice, 3 f thrice, and so on. So we can just keep applying f to x. And this is how we use numbers, right? These are also called piano numbers, if you want to Google about them, by the way. So yes, let's do this. Let's get 0, right? And now, what 0 is just taking f, taking x, never applying f to x. We can have 1, right? So 1 just applies f to x once. Fine. We can have other numbers as well. We can have 2, we can have 3, we can come here, we can do this, we can do this and this, you know. Quick and easy. You know, just some vim, you know. Okay, cool. So now the thing is, these just repeat the functions that are passed to them, which means that we have a function which does something. All right, so I'm just going to have a function which I'm going to call do something, and it console logs something. Yay, nice. So do something is going to do something, right? We can also do something twice. And for us to do something twice, we just need to repeat the do something function 2 times, right? So this is do something. And now if we do something twice, something, something. Cool. So I'm just repeating whatever function I pass to my numbers. And these are, in fact, once, twice, or thrice, if you'd rather think about them this way. Okay. So with this, I'm going to do something which is going to help us to convert those functions into the representations we're used to, right? Into integers, into like decimals we're used to. So let's just do a toNum function. That's just going to take a number function. And what it's going to do is it's going to have a counter. This is not really pure. The only reason why I'm having this is because I want to convert the functions to something that we understand, right? I'm just doing this so I can get the result out of this system, out of Lambda Calculus, right? So I'm going to have a count, which starts at 0. I'm going to pass the function to number function. And it simply increments my count every time it's called. And then I can console log count. And now if I do toNum, I can do that for 1. I can do that for 2 and for 3. 1, 2, 3, cool. Let's do 0, just for the sake of it. Cool. Okay. And now that we have numbers, well, why not replace arithmetics, right? I mean, don't need booleans, don't need integers, don't need that kind of thing. So first to replace arithmetics, we're gonna start with the simplest thing we learned in school, a sum, right? Just take A and B, right? The two numbers you're gonna sum. And now I'd like to ask you a hard question. What is a sum? Like, what is one of the ways you can think about sums? Well, you can think about it as getting the successors of numbers, right? So if you have 4 and 2, what you're doing here, you can think of it as if you were getting the successor of 4 twice. You're getting 5, you're getting 6. That's what you're doing. So you're getting A and B, and you're getting the successor of A, B times. Now, well, we don't have the successor function, so we need to implement it. By the way, the only reason why I'm using variables here is so that it becomes understandable. I don't want to write a single line with these things. Not sure that would be nice. So let's implement the successor function. We're going to have a couple of steps. I'm going to start with the most basic one. So I'm just going to return whatever I pass to this function. And I'm going to do toNum successor of 2. There we go. So this should give me 2, right? Whatever number I give to it, it will just give me that very same number. Cool. Now, what if I always wanted to return 1? Well, let's just copy the definition of 1. Right? Why not? Let's put this here. Okay, so if I save this should give me always 1. Doesn't matter what number I pass in. Right? If it's 2, if it's 3, doesn't matter. Right? Always 1. But the nice thing about doing this is that now I have access to f, which means I can play with f. I can apply it as many times as I want, right? So what if I repeat f n times? I start getting the exact same number I pass in, right? And now, well, how do you increment a number? You just apply the function once more. So we just apply that to f. And the successor of 3 becomes 4. You can just get this. We can put this in here. You can have 4, and that's 4. Great. Now we can go on. We can have our sum. We can define here 5 as the sum of 2, 3, and we can do 5. Cool. Now, next thing, multiplication. So, multiplication, right? What is multiplication? Well, we can think of it. So we already have functions which multiply things, right? We have A, we have B. So if you do A times B, you're just multiplying B by A. Now the thing is, you want B to multiply 1. You want B to multiply F, right? Because you want to do B times 1 and then that times A. Because you need to multiply something because you have a function.
It's very hard to see the comment.
Ooh, okay, let's just make it not compile. Okay, cool, thank you. So then multiplication is going to become taking A, taking B, and taking F. And now what you do is repeat F B times, and then repeat that A times. And this is multiplication, so you can now do 6 as the multiplication of 2 and 3, and you get 6. Okay, now exponentiation. That's why we use F here, because for exponentiation, we already have functions where we repeat things, as I've said. So if we want to do 2 to the third, what this is really 2 times 2 times 2 times 2. We're just repeating a function which repeats something, repeating something, right? So exponentiation is simply taking A and B and applying it to B. And now we can come here, we can do this, we can replace this by 8, can do the x thing, and now we have 2 to the third, and hopefully this is going to be 8. Cool. Subtraction. So what is subtraction? Well, subtraction is a lot like a sum, right? So if a sum is getting B times the successor of A, subtraction is the opposite, right? So it's getting B times the predecessor of A. Now, well, we don't have the predecessor function. Okay, let's do this. This is a bit more complicated. I mean, we're going to get there, okay. So for that, I need to explain what I'm going to call wrappers. This is not really the correct term. I like to call it that way. It's easier to understand. We're going to have pairs, or tuples if you prefer. We're gonna then increment those pairs, and only again then we get to the predecessor function, right? So first things first, wrappers. So if you're gonna wrap something, right? You can also call this apply if you want. So we're gonna store something, right? So we're gonna pass a to it, and then when we pass f, we're gonna apply whatever is stored to that function. So let's just do this, right? Let's get what I'm gonna call a wrap here. I'm gonna take a, I'm gonna take f, then I'm gonna apply a to f, and now I can have what I'm gonna call a box. That's just an easier concept, which wraps Serbia. There we go. And now if we do box console log, what happens is we already have Serbia here, so Serbia is kind of like a. So when we pass console log, we'll be doing this, right? Console log Serbia. Okay. So if I do this, we get Serbia. Cool. And put subtraction function here. Okay. Now pairs. Well, a pair is just really a box with two things inside. So we have a pair which takes x and y, takes f, and just uses f to select one of those items. So we store two values, tell which one we want, really easy. And we already have functions for doing that, true and false, right? So true just selects the first thing you pass to it, false selects the second. So if you have a pair, right, then you use f, and f is going to select either the first or the second thing, and we're going to be fine. So you can get values out of our box. So now I'm going to have here a pair function. So our pair function takes a, takes b, then we do f a b. Cool. Now our box can have a pair, Serbia and Brazil. Okay. Now we can do this. We can select the first. We can do this. We can select the second as well. So you can have both. You can come here. We can do this. We can do console log. We can go to, I also need to do this. And then I go to the end line, put this and this. So we now get first is not defined. Oh, yeah, of course, because I call them true and false. Let's define them. Let's get true and false. Let's put them here. I could just have done other thing, but it's fine. So first equals this. Second equals this. Then I get here and here. So I have true and false. And now I can get the first and second finally. Cool. Easy, right? Everyone okay? Okay, cool. So now that we have this, we can increment pairs, right? It's the name I like to give it because it's easier to think about it that way. So this is not really incrementing a pair. What it's doing is it's getting the second item, putting it into the first position, incrementing the second item. So you go from 0, 0 to 0, 1 when you increment it, 1 and 2 to 2 and 3, 4 and 5, anyone? Anyone? Perfect, 5 and 6. And well, the interesting thing is that if you repeat the increment pair operation 5 times, for example, over 0, 0, you see that we get to 0, 1, 1 and 2, 2 and 3, 3 and 4, 4 and 5. And the first item here is the predecessor. Ta-da! Okay, so now, bits by bits, first, increment pair. Takes a pair P. Now, how do we get things out of a pair? Well, we use first and second. So we get a second item, we put it into another pair. Then we get a second item again, second, and now we get a successor of that. Increments a pair. Okay? We can have a pair which I'm going to call 0, 0. That takes a pair with 0 and 0. Whoop, 0. And now, what I can do is I can use increment. Let's do another thing. Let's do a variable called result. And now let's use increment pair over 0, 0. Cool. So now that we have that, we can console log result. We can have yes and no, yada, 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 all that thing. Okay. This needs to be lowercase. Okay. So result. This doesn't need to be yes or no. What am I doing? Oh, sorry. So to num result, let's get first, second. Okay, better. So I'm going to increment the pair 0, 0. I'm going to get the first thing inside that pair and the second thing, right? So if I do this, 0 and 1. If I repeat that twice, I get 1 and 2. If I repeat that twice, oh, 3, sorry. 2 and 3. Okay. So now we can implement predecessor, which is taking here a number n. It's going to use n to repeat the increment pair operation n times over 0, 0. And now I can define 7 as the predecessor of 8. And I can do to num 7. F is not a function. Interesting. Why? I'm doing the predecessor of 8. Do I have 8? Yes, I do have 8 n times increment pair over 0, 0, of course. First, result is not defined. When am I using result? Here. It's not in the screen. Okay, 7. Cool. Yeah. Okay. It's got me nervous for a bit. It's fine. Having some fun. Yeah. So, next thing we're going to do. Oh, subtraction, of course. I can just uncomment this. Put this here. Let's just quickly test our subtraction. So let's use 5. Let's use 2. Okay, it works. Nice. Okay, we got a predecessor function. So it's just getting the first thing out of n increment pair over 0, 0. Right? Predecessor of k is n times its subtraction. All that we've just seen. Right? All good. Amazing programming language. Do this, do this like in your job tomorrow. Amazing. Your coworkers are going to love it, right? Everyone's going to be like, oh, this code is so nice, like so composable, like composable, to the last level of composability. Okay, so now let's replace Boolean operators. Okay. Well, first thing, let's get to replace and or. You can also have an if, by the way, which I didn't do up there. So if is the simplest thing ever. Let's just do console log, the usual yes and no. Oh, I'm tired of that. Okay. So basically, if is just really syntax sugar here, because if you already have a Boolean, you can just like return that Boolean. So just the identity function is not really, that much fun. Let me comment these lines. Okay, so this just returns whatever Boolean you pass to it. That's just really syntax sugar in this case. It's not really a Boolean operator, but anyway. So we can have AND, so it just takes A and B. And well, if A is true, it returns the first thing that's passed to it, right? And what do you want with AND? Well, we want both things to be true. So let's just return B. So if A is true, returns B. B must be true, otherwise it would have returned false. Otherwise, it can just return A, because if A is false, returns the second thing. Well, A is already false, return false. Easy. Then we have this, which is OR. So we just take A and B. So if A is true, we can just return A straight away, because we only need one true thing. And then otherwise, it would return B. If B is true, A is not, well, we get true anyway. That's fine. Let's test these. Let's have AND true and true. Copy this a couple times. False, true, false. Okay. So this should give us true. This should give us false. This should give us false. So yes, no, no. Cool. Now we can also replace these with an OR. Now this should give us true. This should give us true. This should give us false. Yes, yes, no. All working, all good. Nice. We have our not, we have our or, we have our and. We can go on. We can have less or equal then. So less or equal then, you want to compare two numbers, right? You take A and you take B. In this case, it's important to notice that we can only work with positive numbers here. There's ways to represent negative numbers, but what we're going to do here only involves these. So you need to see here that if we subtract two numbers that are equal, they're going to return 0 in the same way that if we try to subtract and it would return a negative number, you would get 0 anyway. So you need to check if the subtraction of A and B is 0. Okay, we need E 0. Let's do it. Is 0. And now there's a nice thing here, which is called alpha equivalence. So alpha equivalence is when two functions, two lambdas, they actually do the same thing, they just have different names. So false and zero are the same thing, right? So they just take two things, return the second one. And by the way, this is the syntax for for renaming things, right? So if you have this expression and you want to rename x to a, you just use curly braces and you can rename things. Cool. Before you go to that, let's do is zero. So is zero basically takes a number and checks if it is zero, right? So when a number is zero, means it's going to return the second thing that's best fit, because zero is just really false, right? So if it is zero, it can just return true straight away. Amazing. Otherwise, we cannot really return false here, because if a is a number, we need to be repeating that over and over. And if we want to create a function which always returns the same thing, we can create a function which has this, true, false. So it will always return false every time it's called. All right, let's test this. Let me comment these. Let's console log. Is zero, so we're gonna have zero, of course. Usual yes or no. Do this. Come here, 1, 3. Okay, so yes, no, because only the first one's zero. Yeah, it works. Now I can have less or equal then, and now we can go back here. We can have this, and now less or equal. Let's do 1 and 2. Let's do 2 and 2. Let's do 3 and 2. And I think that's it. Let's actually do 2. That's fine, actually. Okay, so this should give us true, because 1 is more than 2. This should give us true, because true is equal to 2. This should give us no. So yes, no. Fine, it works. Can go on, implement equals. We can take a and b. So now we can have an and, right? So if both a is less or equal than b, and now if b is less or equal than a. Okay, that's nice. Okay. So this means we have something that's equal. All right, we have two equal numbers. Let's jump right here. Remove these. So this is not really equal. This is equal. This is no. So let's put this on the top. So we have yes, no, nope. Yes, nope, nope. Cool. Can also do greater than. So greater than takes a and b. Well, greater than is just the opposite of less or equal than, right? So it's just the opposite of checking if a is less or equal than b. Because if it's not, well, then this should return true. So now it's going to invert that, right? So you can just come here, replace this with gt. So not g and t, gt, okay? So true, or 1, 2, this should do no, yes. No, yes. Okay. Okay, now Lisp time. Let's get a function. I'm gonna get this one, put it here. So I have a function, right, which does things, right? That's what functions do, things. It takes a and b, has 3 conditions. So these numbers make it go through each one of these paths. So if a is equal to b, a times 2 plus b. If a is bigger than b, it does a minus b, otherwise a times b, right? That gives us 9, 1, and 12. Cool. But the thing is, right, I mean, too much syntax, right? I mean, keywords, this, like 2019, not really a thing. I mean, have you heard about Haskell, by the way? So we have a function foo. We're going to make it curried. I'm going to make it take a and b. Now let's replace things, with, real programming languages. No, just kidding. So equals a and b. So if a is equal to b, we're going to get to the first branch. So we're going to do this. Now, too much syntax. We're going to multiply a by 2. Replace this with 2. We're going to sum to that b here. Okay, let me check the parentheses, So if a is equal to b, we get here, we do a sum. Parentheses are right here, here, and here. Otherwise, we have another if. So this else if does a comparison to see if a is greater than b. More parentheses, it's my thing. So we have if a is greater than b, then we can just do subtraction, a, b. Otherwise, we come here and we do mult a, b. Parentheses right, parentheses right, 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 right. Oh, good. Okay, this. Okay, we have a nice function. I think all the parentheses are right. Hopefully, this is going to be like very difficult to debug otherwise. I mean, it's really composable though. So let's do 2 num. So now, we can do this. Oh, let's just do this. Oh. And then this. Nicer. Replace things, Really happy. Okay. So we have our function. We have 3, 3. We have 4, 3, 3, 4. Exact same thing, Thank you. Okay. Now, not really hardcore. Birds time. So what are birds? Well, birds are just combinators. So combinators are functions that don't have any free variables. So in that first function there, which is called with context, you have b, which comes from the context. You have a, which is bound to the argument. Right? So that's not a combinator. Second thing is a combinator. So you get both an a and b being bound to the arguments. This is a combinator. Only x comes from the argument, combinator, right? All of them are bound. Here we have y, which comes from the context. It's a free variable. Here, anyone? Combinator or not? Not a combinator. Okay, cool. 4, so 4 is a combinator because both x and y are bound to arguments. Easy. Now, why do we have bird names for those things, Because of this amazing guy called Raymond Mullion, which has written this book called To Mock a Mockingbird. It's an amazing book, and basically what he does is he explains combinatory logic using names of birds for combinators, and he asks you to prove properties about his forest using those combinators. So it's just really a puzzle book, and it's amazing. I highly recommend. So we can just start giving bird names to our combinators. So we have the idiot bird, or the ibis, which is just our identity function. We have the kestrel, which is just true, so it takes 2 things, returns the first. We have the kite, which is just false, takes 2 things, returns the second. We have the cardinal. Cardinal is just like not, so it takes f, a, and b and applies them in reverse order. We have the video, which is just pairing like tuples. So we get f, a, and b, and then we apply b and a to f, right? We have multiplication, which is the bluebird. So bluebird is just function composition, and the very elegant thing that we have here is that multiplication is really just function composition in Lambda Calculus, right? So you take f, g, and a, and basically you apply a to g and the result of that to f, like really, really elegant. You have the thrush, which is just our wrapper, apply. We have the Starling. This is a bit more complicated, so you apply x to g, and you apply that to the result of f of x. Really nice. And we also have the y combinator. So this is why the accelerator in Silicon Valley has the name it has, because y combinator is just a combinator that allows you to have recursion. And this is exactly what they do, right? They are a program that runs programs. That they are a company that help other people start companies. I have a post about that. Go to lucasfcost.com. Great post, I really like it. And well, now we can just start replacing our functions with the combinators, right? So in the successor function, what we're really doing is composing n of f with f, right? And then we can remove this and just have the bluebird. of f and n of x, because it's just function composition, right? And then we can go even further, and we can use the starling to just have the starling of the bluebird, right? Because we're going to apply x to g, and the result of f of x. And I know this is really cryptic, but it's going to be fun, you know? Like, addition is really just like successor we've just seen, you know? Like, starling the bluebird, you know, addition thing, you know, easy, right? I mean, everyone wants to do that. And why not? So let's just get our birds, you know, all of them, you know, let's put them here. Let me give them a bit of space, you know, birds need space. Okay, so let's start replacing things, you know, let's start replacing our if with the ibis, you know, we can come here, we can replace true, let's replace true with the kestrel, let's replace false with the kite, let's replace not with the cardinal, you know, all that. Let's get successor and sum, let's replace those as well. Same results, see? You can just use birds, you know. I mean, your code base would be like so much better, right? Really practical. I mean, who wouldn't want that? Okay, so you can run JavaScript and the birds. Next level, right? So all those birds, you don't need them. You just need two, right? You just need two combinators. You just need S and K. You just need the starling and the kestrel. And that's what we call SK calculus. Because those are already Turing complete. You can write everything. You're only using S and K. Right? Why would you use in your, can you imagine a keyboard? SK parenthesis? Amazing. Like, how much money would we save in keyboards, right? Come on, capitalism, please. Like, some people also call it the SKI calculus, because, you know, it's more convenient to have I, because very convenient, right? You know, come on. You know, but I is really just SKK. Perfect. You know, if you want to do the kite, you know, KSKK, or more elegantly, if you have I, KI. KI, nice. Bluebird, SKSK. Cardinal, come on, easy. Easy. No one? Come on, guys. Really? SKSKSKSKK. Right? Oh, God. You know, you can find all of these birds in this amazing list. They have many more combinators than what I have. You know, it would be a lot of fun to implement all of them, but we would be here till tomorrow, maybe. I don't mind. But what does this mean? If we can replace all code by functions, all functions by combinators, all combinators by S and K, we can replace all code by S and K, right? Why not? I mean, come on, tomorrow, just get to work with that, like, you know, 3 keys, you know, parentheses, 4 actually, because we need 2 parentheses, right? Parentheses, SK, amazing. People have actually done things for you to explore with that, you know, Lambda Calculus, you know, there's an amazing post about combinators in the second link, you know, you can find them later. I'm gonna put them online, don't worry. And well, you know, let's just do it, you know. Just do SK here, get some birds. Let's get these. Let's put them here. Let's remove the ibis. We already have the kite, we already have the bluebird. Same thing, see? Just S and K. And well, that's basically it, but I would like to apologize because I might have completely ruined your night. I mean, but it's Friday though, you know? Can go out, it's fine. So this is really just like a gateway drug for, you know, wanting to hang like good pictures in your room. Amazing. Like, this is like so great. It gets you introduced to many like philosophical themes and also like themes in the realm of programming. It's really a fascinating topic. Sometimes us programmers don't realize how much we have to do with philosophy. You know, just Google Laplace's demon, you know, tomorrow, not today, right? Laplace's demon, just do that. And it's gonna just blow your mind, really. And well, that's pretty much it for me. So these are a few references, do take pictures, they're all amazing, right? So all of them are really, really great, you know. These talks There's also lectures from ASU, Arizona State University, which are absolutely amazing. And well, that's pretty much it for me. You can follow me on Twitter, on GitHub. You can go to lucasfcosta.com, read the things I write, tell me if they're good or not. And I hope you have enjoyed this. Thank you. First question, is it practical? Yes.
Oh, wow. Magic promised, magic delivered.
Can I take my shoes off?
Yeah, sure.
Sorry, I'm really like, you know.
So, it was really silent for a first half of an hour, but we do have questions. First question, do you use any compiled to JavaScript language like ReasonML, ClojureScript, Elm, PureScript? Question mark.
TypeScript.
Can you recommend something?
Lambda Calculus, SK Calculus, amazing, very productive. Highly recommend. But you know, do use types though. Types are great. Use Haskell too. It's very nice. Lisp, yeah, Lisp. You know, many parentheses. You know all about parentheses now.
Okay, next question. What is your opinion about Lambda JS? Do you use it?
Actually, yeah, I don't. I use -fp a lot of times. That's mostly because like we already use -fp like for a long time, and you know I just use -fp most of the time. So yeah, I don't really have a very strong opinion on that. I mean, if you know the principles of functional programming, you can apply them to basically anything. You know, like the thing is, I'm sorry if I'm talking too much about Haskell in a JavaScript conference, but the thing is, once you like learn things like Haskell, you start applying some of those concepts to JavaScript, and it's really like it's much more about making decisions. There's no bullet like a silver bullet thing. It's just like if you know it, you just start applying those patterns to many things. You know, you don't need like all those complicated names really. You know, it's good to know them so you can talk to people, because they're just like symbols we use, right? It's all about giving names to things so you can talk about them. But yeah, do learn like functional programming languages, and you'll be able to do JavaScript in a much more functional way. It's going to be fun.
Fair enough. Next question. How can you make it easier to debug the parentheses, question mark, smiley face?
I don't make mistakes, so I don't have to debug them. No, just kidding. I just let it crash and rewrite everything.
And the last one is SKKSKS, question mark.
S. K.
Yeah, yeah.
So SK parenthesis, close parenthesis, open parenthesis K, close parenthesis, open parenthesis S, close parenthesis. No, yeah, I got it right. I don't need to debug things.
Perfect.
See?
Perfect, perfect, perfect.